Hi, my name is Xueyi Zhou. This video introduces IMPsys, an intelligent mode processing system for smart factory. To be noticed, the mode in this presentation stands for mode component. Current mode factories are facing with a challenge that there is no public or private system which can not only manage the information of the processing orders and factory's machines, but also automatically export jobs, infer the possible process time for each procedure on each mode, and schedule the processing jobs. In this paper, we propose a web-based system which combines the overall streamline of mode components manufacturing. The system is expected to not only contain the staff, order, and device management section, but also detect the processing positions, clarify the process types of the relative positions, estimates the processing time for each process type in terms of a specific mode, and schedule the processing jobs. In our system, we utilize three kinds of methodologies to realize the automation. The first one is a deep learning method called YOLOv5. We transfer the model from object detection task to position labeling and process type classification task. The second one is also a deep learning method called FusionNet. We utilize it to infer processing time of each process type in terms of a specific mode. The last one is a 3D algorithm for job scheduling. About the job exploration, we simplify the task from 3D model labeling to 2D object detection. We transform the 3D models into 2D images by using PyVista. Basically, we get 3,108 images from 518 models and their normalized depth information at the end. Each image is additionally labeled with bounding boxes and machining types by human experts. As the object detection model YOLOv5 is not enough for us to extract machining features because, in this case, YOLO can detect only A, B, E machining features. So we specifically ensemble two multi-label classification models with the object detection model. We get 4 outputs from the models where 2 logits are together with a confidence score vector and a bounding box vector. Next, the vectors are flattened and put into multi-label classifier. Let's take an example. When the second 2D image is being started, it sequentially goes through 2 classification layers and the object detection model, and the system ensembles the outputs together in integrated output vector. The vector goes through the classifier to get possible machining types. Also, the object detection model outputs the bounding box position. If output value of label is over the threshold, the label is true then. About the process time inference, after we know which types of processing should be performed, we need to know how long it takes to process. To solve this regression problem, we initially extract several features of 3D models, such as additional metadata for each mode obtained by PyVista library. The information acquired includes cell, point, X bound, Y bound, Z bound, and volume size. In addition, a simple rectangular volume covering the entire process is created to determine how much the total grinding was in the process, and the grinding volume was calculated by Boolean operation in the existing box and used as meta information. Later, a rectangular box is created enclosing the entire grinding surface, and the subtraction operation is performed on the current mode data. Finally, we get both 2D conversion images and spatial meta information as regression model input. Then, we integrate both spatial information and metadata into a table as our dataset. Next, we generate several 24x24 images for reducing dimension of input data without losing so much information. Specifically, all vertex information is converted into 2-dimensional coordinates xy by applying the principal components analysis, so we can get the key parts of the model which are highlighted in the images. Images generated have many unnecessary information such as the lines and points as shown on the left. In order to utilize the vertex more among the face and vertex information of the same color, We transparentize the lines and perform post-processing to reduce the line thickness. As a result, the processing parts are highlighted as much as possible, and unnecessary parts are reduced. Then, we use the collected features and transformed 2D images as input for the FusionNet model, which consists of 2 layers of MLP and a multiple regressor. After being trained, the model outputs the floating numbers standing for processing type as expectation. Since the process time is predicted, we expect to use them for scheduling jobs. In this case, we use a greedy algorithm method. Each job is a tuple including order ID, mode ID, process type, and ordinary process time. We first confirm the priorities of the process types, then we cluster the jobs into job list on process types, and order each job list according to the priorities of the modes. We also generate 2 tables to show the idle time and other necessary information of devices and modes at the initial step. To simplify the algorithm, we set all the initial idle time as 8 AM here. Then we combine ordered job list into a job queue. When the system gets the first job from the queue, it first fetches the fastest available machine and the idle time of the mode, then calculates the real processing time of the job by dividing ordinary process time into efficiency. After placing the job on the Gantt chart, the system also updates the idle time of both the device and mode in idleness tables. In this case, we get the first job, mode 1 from order I waiting for processing B with 1 hour. As the first fastest available machine M1 is with the efficiency of 100%, you could easily know that its real process time is 8 hours. According to its relative mode is available at 8 AM. We could know that the first job starts at 8 AM and ends at 9 AM on machine M1. When the jobs of process type B are finished, the system turns to the jobs of the process type A and starts scheduling again. In this case, as the relative mode is likely to be processed before, the job will start at the latest idle time of either the device or the mode. In this case, the idle time of the device is 8 AM. However, the mode will be processed on M1 at that time. The job thus starts at the end time of the first job, aka 9 AM, on M3 and ends at a quarter to 10. Following those progresses, the jobs will be scheduled quickly and efficiently. We developed the system based on a very classical architecture. The backend is mainly supported by Django RESTful framework, and MyCircle. We decouple the connection between the backend and the AI models by message queue. We also protect the server gateway and balance network load by meticulously designed firewall policies, UVSCI, and Nginx. We built an interactive interface mainly by Bootstrap and jQuery. This is the core structure of our system. The system is basically available on different ends by browsing the web pages. After going through the gateway, one of the hosting services handles with the request. Those services are of master work mode with 4 main sections respectively: their views, an API, transaction, database operator, and message queue operator. To handle with the massive data, we deploy MyCircle clusters on our servers. Message queue hosts the queue of task IDs. Subsequently, we deployed 3 kinds of the message queue consumers for each kind of the task to consume the task IDs. We show our system by a screen recording. First, we need to log in the system and create a new machining order. Here, we should input the order's title, description, and upload the 3D models. Next, we click the predict button to supplement the model information by JE and PTI. To schedule the jobs on different devices, we should define the devices first. In device board, we could retrieve the device list and add a new device. After the processing time is inferred and device list is set, we could directly click schedule button to schedule the jobs. In our system, you could click machining type-based timelines for checking daily, weekly, and monthly timelines. Rather than checking periodic timelines, we could also browse the timelines of a task. That is all for our work. Thank you for your attention.